The slow, inexorable migration of plastic into every aspect of our lives goes on day after day, as petrochemical companies race to construct even more plastic-producing factories and international efforts to stop the flow of plastic fail year after year. At the same time, concerned scientists around the world are working to determine what all this plastic pollution is doing to our health, our food supply, our water, and the future of our planet. One of those scientists is Dr. Christy Tyler, professor at the Thomas Gosnell School of Life Sciences at the Rochester Institute of Technology. Doug and I caught up with Dr. Tyler earlier this week and asked her first to talk about how she became interested in this field. Here's our interview with Dr. Christy Tyler.
I grew up in Syracuse, New York, and I went fishing with my dad a lot and would be very curious about how fish work or how the environment works, how to be outside. I always liked water. I think as a younger child, because my father was a doctor and I knew I didn't want to be a doctor, I wanted to be a veterinarian. So that was my goal for a really long time. And then in high school, I worked for a veterinarian and decided that maybe wasn't what I wanted to do. And then I got into college and took a course in ecology. And that was really exciting. I did some study abroad. And then I finally took a course in ecosystem ecology as a senior. And that was it. From then on, it really was, how do ecosystems function? I was particularly interested, in all of my graduate work was on land margin ecosystems, estuaries, salt marshes, shallow areas where the dynamics are really complicated because you have this interface between terrestrial and water, and also where there's a lot of impact because there's usually a lot of people that live at that land margin.
That's where people want to live.
Yeah, sure.
Right. It's a beautiful place to live. And so we are now dealing with the fact that a lot of people want to live in those areas.
Okay. So, Christy, how did you become involved in the whole issue of micro and nanoplastics?
At the time that I started becoming interested in plastics was a time when I was looking at the impact of engineered nanomaterials on ecosystem ecology in the Great Lakes, particularly Lake Ontario. And my colleague here at RIT, Matt Hoffman, who's an applied mathematician, was doing some modeling to assess the potential input of plastic to the lake, and also some of the transport modeling, which was showing that most of the plastic in the lake, rather than accumulating in a big garbage patch out in the middle of the lake, is moving back closer to shore and sinking to the bottom. And that's the area of the lake that I study, shallow, close to shore systems. So that was a really great opportunity to collaborate. We teach a course together. And so this provided a really nice opportunity to develop a project on the impact of plastic on the nearshore region of Lake Ontario.
That's so interesting that you're talking about the gyres and where you saw these huge patches. That's how most people first became aware of the problem of plastic in our bodies of water, was with these gyres in the oceans. This is interesting that in the lakes, is it true of all the Great Lakes that the plastic is actually moving toward the shore and, depositing itself in the sediment there?
That's what the models show, because we don't really have big gyres in the Great Lakes.
Right.
The circulation patterns are different. And there's also issues with the density of water being different. So seawater, because it has salt in it, is more dense, which means that more of the plastic floats. And in freshwater, more of the plastic will sink because different plastics have different densities. But most of them are right around the density of water. Some are a little more buoyant, some are a little less buoyant. But because of that density difference between seawater and freshwater, there's more of them will sink. And once the plastic's aged in the environment for a while, it's more likely to sink.
And does that sinking affect its degradation?
We haven't looked specifically at whether or not a sunk plastic degrades more. But a lot of the degradation is due to UV radiation. And so something at the surface of the water is likely to be more oxidized. And we have seen that. The plastic that's at the bottom, particularly once it gets buried in the mud, there's no UV radiation.
Sure. Yeah, that was my hunch, and hence my question. I was just curious to know if you had taken a look at that.
Yeah. How is it impacting the aquatic life in the lakes?
So some of the research is pointing to shifts in carbon and nitrogen cycling. You get the formation of a biofilm on the plastic. So microbes and algae will grow on the surface. And so you see different species on the plastic than you do in the environment. You can have higher densities of things like pathogens that grow on the surface of the plastic because it's a different environment. Those types of pathogens are often more competitive on growing on a surface than they are free floating in the water. So there are a variety of ways, but I think there's so much that we don't know. I mean, we don't know if the plastic that's accumulating in fish is harmful to the fish. There's more evidence that's pointing to it being harmful, but it's also a really important thing to separate the plastic itself or the particle from the chemicals that are associated with the plastic because they're different and the modes of impact are different from a toxicology perspective. A particle is a different thing than a dissolved chemical.
So how do you tease that out?
You can do experiments where you leach the particles and then expose animals to the leachate. So we've done that. A lot of our work, we use a very small aquatic worm that's abundant in almost all freshwater ecosystems. And so they're a really easy test animal because you can easily look at their response rate and their growth rate or their heart rate and try to understand the effect. So if you do experiments where you've got the particles with whatever has leached out of them, the chemicals, and then you just have the leachate, you can compare the effects of the two. And the polymers also have very different shapes and sizes. A polyethylene terephthalate, which is polyester fiber, has a different potential impact on small animals than a tiny particle, like a fragment of plastic. So animals can get entangled in the fibers.
Sure. Yeah.
That was my next question. And have you actually figured out the major sources of plastic contamination, in the lake that you're studying?
So we believe that stormwater runoff is probably the biggest source. And we've been doing a lot of measurements of stormwater input of plastic and then trying to scale that up to the total numbers of storm drains and the total numbers of rivers and tributaries. It's really difficult to go out and measure microplastic particles and say, well, this came from a Snickers bar wrapper or a bottle cap or a cigarette. I mean, a cigarette butts are probably the easiest, but we don't find a lot of those materials out there, even though cigarette butts are actually one of the major sources of plastic pollution in stormwater.
So that's so interesting to me. So not wastewater from a sewage treatment plant, but stormwater runoff from the land.
Right. So if you think about the plastic that's coming into the lake from a wastewater treatment plant, that's all going to be very tiny particles. So if you were to count the number of pieces from a wastewater treatment plant, it might be very high. Mm-hmm. But in stormwater, you're getting big plastic that eventually may break down into millions of teeny tiny particles. So in terms of the mass of particles coming in or plastic coming in, the stormwater has macroplastic, which is big pieces.
Can you talk a little bit about the litter traps? I was reading a little bit about that on the website.
Sure. So a litter trap is basically a basket with a 5 millimeter mesh in it that is installed into a storm drain. And so when we started this, we put in 9 of these, and that was supported by 2 separate projects from NOAA's Marine Debris Program. And we monitored those for 2 years. And one of the most interesting parts of that study, which was conducted primarily by our grad students, is that it's incredibly spatially variable. What you find in the litter traps, the abundance of material, and then the characteristics, like what is it, is really variable. So it can vary by an order of magnitude, and then the composition of the debris varies on a block by block basis in the city. So with that data, we've then moved into 2 separate avenues, both of them kind of informed by the idea that it's really variable. So any solution you put in needs to be really targeted and kind of hyper-local to where you're trying to make an impact. Mm-hmm. So One of the new channels is a project that's also funded by NOAA. With that project, we're taking a model that was built by one of our graduate students that predicts the amount of plastic entering a storm drain using spatial characteristics and temporal characteristics, rainfall, but also what are the characteristics of the location, particularly things like, are there venues that sell food? What is the socioeconomic status? How many people in the area smoke? And it predicts the amount of debris. And so we can use that to figure out where the hotspots are.
Yeah.
And then be strategic about where you install interception devices, because you're not going to install a trap in every single storm drain. And
Sure.
even just in the city of Rochester, there's 30,000 storm drains. So it quickly becomes an intractable problem if you're trying to tackle it that way. So the hope
Sure.
is that with building a good model, we can target the areas of the city that are hotspots of debris and that also have the potential to impact downstream resources that are sensitive, because not all storm drains go directly out to the environment. A lot of them go to the wastewater treatment plant and the debris gets treated and the big stuff gets removed. Some of the microplastics will end up getting through, but usually the removal rate is pretty good.
Is the lake a source of public water supplies for some communities?
It is. Yeah. In Rochester, we get some of our water from the Finger Lakes and some from Lake Ontario.
I know that vehicle tires, Christy, is one of the primary sources of microplastic pollution. I'm assuming that those microplastics that are coming off tires are going right through the mesh of the litter trap so that you wouldn't necessarily pick those up. Is that right?
That's true. The company makes a liner that's got a 1 millimeter mesh, but we don't use those because you capture everything. It's not just debris.
You're capturing everything when you have a fine mesh like that.
Yeah, but it's also leaves and grass clippings and rocks and anything that's flowing with the stormwater is going to be captured. I think once the bottom of the basket's coated with leaves and grass clippings and debris, we are capturing microplastics, and so they are getting taken out. But really, we're focused on the big particles and big pieces of plastic that would be entering.
I'm going to guess that a lot of it is food packaging, because we know that's a significant source. And of course, that's one that we might be able to address with different ways of packaging our food. Can you take an educated guess as to what percentage of the stuff you're finding in these traps that are in residential areas are coming from
including
food
candy
packaging?
wrappers and, know, chips bags and that kind of stuff?
Wish I had the number off the top of my head, but of the items that you can actually identify, the two categories that are the dominant ones by far are smoking products, including cigarette butts, but also cigar wrappers, and the cellophane wrappers on smoking products are really, really common in certain places, and then various kinds of food packaging. So wrappers, bottle caps, little condiment containers. These are storm drains and they have a grate on the top. So those are the bigger things. And those bigger things are typically caught up by street sweepers. And so those would not be getting into the stormwater system in the first place. They're still in the environment, and that causes all kinds of issues and aesthetic problems and environmental quality issues, but they're not necessarily getting into the lake.
So plastic water bottles are going to get caught ahead of the trap.
They may. We do find some. Once they've been run over, they can fit into the grate.
Yeah.
But we don't usually see a lot of bigger items. A lot of it is the smaller materials. But we find all kinds of things. When people can have little air fresheners in the car, and you'll find those on the ground. There's a lot of drug paraphernalia that you find. And it ends up being almost like a little treasure hunt when you're going through these. It's kind of gross. It's not really glamorous work, but it's interesting what you do find and how variable it is. With the cigarettes, I think all of the regulations about not smoking indoors have pushed smoking outdoors. And I think people are concerned about putting a cigarette in the garbage because they're worried about it catching the trash on fire.
Sure.
And so it's considered safer to put it on the ground and kind of stomp it out. and leave it. And I think there's also a lack of recognition that a cigarette butt is actually made of a semi-synthetic polymer that is toxic, especially when it's coated with tar and other chemicals. So I think that that's a big one, especially outside of bars. The number of cigarette butts that you find is huge. That'll be the dominant material in a lot of places.
So with all of this work that you're doing and these interesting findings, are you doing any kind of a public education campaign so that people understand that, they need to change their behavior in order to protect the quality of their drinking water?
That's our job, Patty.
I know, but whatever.
I'm talking to you.
She's got to do some of it.
Yes. So that's the other avenue that we took with our initial findings about spatial variability, is to do more targeted community engagement. We started in Rochester, and the goal with that was to install litter traps at educational outlets and then engage with youth to have them do the sampling, they do the sample processing, they do the data analysis, and then they can develop their own campaigns that are local to their community based on what they find in the traps at their school. And on our staff at RIT, we have an environmental education specialist who's developed a curriculum around this. And then we also work with a branding and marketing specialist who comes in and teaches the children about audience and how do you tell your story and what are you trying to get across and what's your message. And then they create promotional materials about their messaging. And it's really amazing. I mean, these kids are, these got 4th and 5th graders using Canva to create flyers that they are able to use. So that program has been really successful, and the kids get really engaged, and they're actually then connected with, the storm drain is connected to the lake. So the water flowing on your street that potentially has trash in it is going to the lake, and that's the water that's coming back through your faucet. So I think trying to connect, especially urban youth, with the water cycle, and the city is as much a part of the water cycle as, a remote valley out in the Genesee River, is one of our primary goals, is just really getting people to understand where the water goes and that they are connected to Lake Ontario, because a lot of urban youth are pretty disconnected from nature and don't see that the city has any connection to the lake.
It's great. It's great when because kids get it right away. Let me ask you about, how do you see the work that you're doing? I mean, clearly there's a worldwide effort here and an imperative to find out what nanoplastics are doing to human health. How do you see your research fitting into that?
So we actually have a project that's funded by the National Institutes of Health and by the National Science Foundation through their Centers for Oceans and Human Health that is focused on microplastics and human health. It's a pretty unique funding mechanism to have it funded both by NIH and NSF. Mm-hmm. And what it does is allow our team at RIT, which is already in and of itself very interdisciplinary, and I'm an ecologist, we have a mathematician, a chemist, an engineer, a biochemist on the faculty that work on our end, to collaborate with the University of Rochester Medical Center. So that collaboration has been a really great way to start connecting the environmental component of plastic pollution with the potential health impacts. And our role is to try to understand input and fate and impact, but with an eye on what is the exposure landscape for people? Where are we finding the most plastic? What form is it in? What type of plastic? Can we trace it back to a source? So that can inform research in the lab on potential human health impacts. And so that's, I think, part of the way that we'll be able to move the needle forward on this, is that we need to know what are the most common plastics in the environment? What types of chemicals are associated with those plastics? Both the ones that are incorporated in the plastic from the production process, and then what might get absorbed onto the surface when the plastic's in the environment. And use that information to guide the human health studies. Because so far, a lot of the studies are either on, do we find microplastics in the human body? Or they're using the types of plastics that are easy to use in the lab and they're pristine, and they're not a post-consumer product. So polystyrene, for example, is really easy to purchase little nanoparticles of polystyrene, and you can use those in experiments, and that's great. And it's informative as a first step towards understanding potential impacts of microplastic. But there's so many different kinds of plastics in the environment, and we don't always find as much polystyrene as we do polypropylene and PET, tire wear particles, cellulose acetate. So being able to understand what are the plastics that are out there and what form they occur in, what kind of microbes are on the surface, what chemicals are associated with them is really important towards understanding what we might actually be incorporating into our bodies.
Christy, are you optimistic about the future? I mean, how do you feel about this? Looking at what you've been doing the past few years and looking out in the future?
I feel like we are recognizing the scope and the scale of the problem, and that's really important. That's a really good first step in figuring out the solutions. At the international level, there's a lot of discussion about how to move forward on various kinds of plastic bans or changes in policy. A lot of those are based on some of the same concepts I was talking about of which ones are the worst, because plastic is an incredibly useful material. I mean, it's in your phone case and your water bottle top, and I'm looking at my computer monitor. It's useful, and it's done great things. I mean, it's kept us safe during COVID. It makes our cars lighter, so we use less fuel. So it's really a matter of figuring out what are the ones we need to be the most concerned about, and then having more guided policy. Otherwise, you either are playing kind of a game of whack-a-mole or trying to demonize an entire scope of materials where some of them are actually really useful, and they make our modern life possible.
Dr. Christy Tyler, professor at the Thomas Gosnell School of Life Sciences at the Rochester Institute of Technology, talking about her work understanding how plastic gets into our water and into our own bodies. You can learn more about Dr. Tyler and her work and find links to our news articles on our program website, greenstreetnews.org. That's going to do it for this week's show. Patti and I will be back again next week with another edition of Green Street. Thanks for listening.